All right, so let's talk about solving what we call exact differential equations. Now, before we go into the process of solving these and what they are, let's just start with, let's go back to the idea of taking the derivative of an implicit function. All right, and this will lay the groundwork of why we do what we do with exact equations. So suppose we have an implicit function that looks like this. And we write it like this to be clear that x is a variable and y is a function of x inside of this implicit function. All right, so when I go to take the derivative of this, I'm going to have to use the multivariable chain rule, which we've used before. Right, it's going to involve some partial derivatives. So the derivative of this would look like this. You take the partial of it with respect to x times, this is the chain rule, the derivative of x with respect to x, which is just going to be 1. Alright, so that will disappear. Plus, then you take the partial of it with respect to y times the derivative of y with respect to x, right? We're finding the derivative with respect to x, and then of course we take the derivative of c, which is 0. Alright, and so what we have is this expression that looks like this, partial of f with respect to x plus the partial of f with respect to y, dy dx. Now we're going to clean this up just a little bit. We're going to call, just to make our lives a little easier, we'll call this function m. I'm just going to write m, although well, I'll write it like this. It's a function of x and y, but we're just going to treat it as m to make our notation a little easier. And then the same thing for here. N as a function of x, it can be a function of x and y, but we'll just call it n. So what this leads to is just this expression right here, some function plus n times dy dx equals 0. Okay, and that looks a lot like a differential equation, right? Of a specific form. In particular, we've got our derivative times some function of x and y plus some function of x and y equals some constant, 0 in this case. All right. Now we're going to do one other thing before we can start talking about this. This is what an exact differential equation may start and look like. But if I just take this and multiply both sides by dx, right, just do a little algebra on it, I actually get this equation. Well, let's do it in non-disappearing ink. Dx times dx, just doing a little algebra, we get m times dx plus n times dy equals 0. All right, now this is the form that will start the process of solving in. Okay, well, we'll come back to that here in a second. So why did we do this? The idea is this. Notice, if I take the derivative of a complex or of a multivariable function, I end up with this, or like we've kind of cleaned it up, something that looks like this or this. So if I were to take the integral of something like this, I should just get the function f, right? If the derivative of this is this, then the integral of this should be this, right? So this is where we start. If we have a differential equation that looks like this, right, or can be made to look like that, our first question is, could it be just the derivative of some function f? If it is, it's an exact equation. All right, now we've got some process to go through to solve this, but that's where we're at. We just start with it. If we start with a differential equation, actually, often we'll start with a differential equation that looks like this, multiply both sides by dx, so it looks like that. And so the question is, once we get to this point, is that exact? Because if it's exact, we can solve it fairly simply. So let's look at an example of this whole process and see it in action. All right, so here's a differential equation we're asked to solve. Oops, let's just clean that up a little bit. And so it's already kind of in this form of a function times dx plus a function times a dy. And so what we need to determine is it exact? Okay. And what we're asking is this just straight up the derivative of some multivariable function? All right. That's what we mean. Is it just a derivative of some function out there? But we don't often think in those terms. We actually kind of have a little process that we go through to see if this is exact. Well, we have one little step to see if it's exact, and then if it's exact, then we have a multi-step process to solve. So step one is when you have an equation like this, or in this form, or if you take the equation that you have and put it in this form by multiplying everything by dx, the first thing you do is you want to check to see if it is an exact equation. That is, if it is just the derivative of a multivariable equation. Okay, so you always do this. Now remember this, we're going to refer to this function as m and this one as n. Okay, so in this process, the m is always the one that's the coefficient of the dx. All right, so here's the test. We take the partial of m with respect to y, and we take the partial of n with respect to x. You got to get these correct, and we ask, are they equal to each other? If they are equal, if those two partials are equal, then this is exact. The reason that's the case is if this differential equation that we're looking at is in fact the derivative of a multivariable equation, then this would have been the partial with respect to x, and this would have been the partial of f with respect to y. That means if I take the second partial of this one, remember this is already a partial with respect to x, if I take the partial of it now with respect to y, we call that a mixed partial. So I'm going to take the partial of this one with respect to y, and I'll take the partial of this other one with respect to x. If they're equal, then that means we've got an exact equation. Okay, so let's do that. So the partial of m with respect to y is just -1, right? Because you go up here, you ignore that because that just get treated as a constant. So you end up just taking the derivative of -y, which is -1. All right. Now let's take the partial of n with respect to x, and it's also -1. And so they're equal. And so, yes, this is in fact an exact equation, so we can go through the process of solving it using this procedure. Okay, so once you've determined that it's exact in step one, step two is it's always going to be the same. Okay, so what we're going to do is we're going to integrate m with respect to x. This is always the thing. And in fact, because remember, this piece should be the derivative of our solution f with respect to x. So if we take the integral with respect to x, we should get the solution that we're after, f. Right? That's what we want. We want the solution. Okay, so in our case, that's going to look like this. F will equal the integral of 4x minus y with respect to x. So y is treated as a variable. The x's are treated as variables. Y is treated as a constant, I should say. So the derivative there is going to be x squared x squared. Let's try that again. It'll be 2x squared minus xy. And then normally we'd put a plus c there, right? Some constant. But this could actually be an entire function of y, because if I take the derivative with respect to x of this thing, it just disappears. Again, the derivative with respect to x of a function of y is just 0. So instead of just putting a constant there, we allow for it to be an entire expression involving y's and constants. But notice what happens. Remember, f is my solution to this differential equation. And now I know a little bit of f. I know that much of it. Plus, I know there's going to be some y terms. There's got to be some y terms. Because look, if you take the derivative of this with respect to x, you should get that. And you do. You get 4x minus y plus 0. All right, so we just take the derivative. All right, so next step after you do that. All right. So we've already got part of our solution, right? Let's highlight this just to make sure. Our solution f to the differential equation is this right here. The only thing we don't know is that g of y part. So step 3 is going to say that is going to be this. Let's take the derivative of our solution, the partial, with respect to y. And wait a second, that should equal n, because that right there is the derivative of our solution with respect to y. So if we actually take the derivative of the solution we found and set it equal to this, those two things should be equal. Okay, so the derivative of the f we just found with respect to y, remember this is f that we just found, so the derivative with respect to y is going to be negative x plus g prime of y, right? We differentiate, let's put that in there again, so negative x plus g prime of y, because if you differentiate this with respect to y, the x squared term disappears. The middle term just becomes negative x, and the derivative of g of y with respect to y is just g prime. So that's the derivative. That is supposed to equal what we already know as the partial of f with respect to y in right there. So we set those equal. What this allows us to do is solve for g of y, or g prime of y, and eventually g of y. So g prime of y, if I add x to both sides, is simply 6y. G is the only thing we're missing from our solution there. So look, I know what g prime is, so if I integrate g prime of y with respect to y, right? If you integrate g prime, you should simply get g. And so the derivative there is 3y squared plus some constant. And that is g, right, that goes up there. Okay. And so let's write our solution. We'll squeeze it in here. Write the solution. And we'll box this off to make it clear here. So the solution is going to be 2x squared minus xy plus g, which is 3y squared plus c. And we treat this as a implicit function, and so we just set it equal to 0. Okay, and that is our solution. All right, and you can check it out if you go back through and take the derivative of this thing right here using right up here, using this right there. Okay, you will see that the derivative is equal to 0. In other words, that plus that will equal 0. You'll see you'll get this exact equation, which is what we wanted, right? And so that represents our solution to the exact equation.